Good morning all. Today we will discuss about electron spin resonance spectroscopy. Electron spin resonance spectroscopy. This electron spin resonance, that is called ESR. So what is mean by ESR? We can say ESR, this is a branch of absorption spectroscopy. And here we are discussing about certain materials like the paramagnetic material, so ESR, it is a branch of absorption spectroscopy where we discuss about some material called paramagnetic material, and they absorb frequency, they absorb frequency in the microwave region. This is very important one. They absorb frequency in the microwave region. Microwave region and undergo transition then the transition between what? The transition between magnetic energy level of electrons having unpaired spin. So for a material to show ESR, we have the electrons that has unpaired spin. That is the necessary condition. We need electron that has unpaired spin. So how can you define ESR? ESR is a branch of absorption spectroscopy where we are discussing about certain material called a paramagnetic material, and what they do, they absorb frequency in which region? In the microwave region. And when they absorb frequency in the microwave region, certainly there is a transition. The next question is the transition between what? Now the transition between magnetic energy levels happens. Magnetic energy level of electrons that has unpaired spin. So what is meant by this paramagnetic material? The material which are weakly magnetized, in the direction of magnetic field. Are called paramagnetic material. So the material that are weakly magnetized in the direction of magnetic field are called paramagnetic material. So in ESR, it's a branch of absorption spectroscopy where we are dealing with paramagnetic materials, and they absorb a frequency in the microwave region and they undergo transition between the magnetic energy levels of electron that has unpaired spin. So, for ESR we must have atoms or molecule having one or more electron with unpaired spin. With unpaired spin. So, for ESR we must have atoms or molecule having one or more electron with unpaired spin. Some examples of the molecule that are showing ESR are NO, then O2, NO2, etc. Then what is the principle of ESR? Next we will see what is the principle of ESR. Now, for ESR we must have an electron with unpaired spin. So, let us consider a free electron. You consider a free electron in an external magnetic field B0 in the z direction. Consider a free electron in an external magnetic field B0, and you assume that the direction of the field is along the z direction. And we can represent it like this. This is your z axis, and along the z axis you have applied a magnetic field and you have an electron. Now, what happens to the spin of the electron? Initially you assume that this is your spin vector, yes. Now, when it is placed in a magnetic field, we know that if this is theta, then this is SZ, that is the z component of your spin vector. Now, we have already seen that the magnitude of the spin vector, is given by magnitude of spin vector S, or this is equal to S. This is equal to square root of S into S plus 1 h bar, where S is a spin quantum number. Also, we have discussed about the magnetic quantum number ms. What is the significance of ms? Ms quantizes the z component of spin vector. So, you can also write this Sz, this is equal to ms h bar. And what is cos theta? You can also define cos theta, this is equal to Sz by S, this is equal to ms h bar divided by root of S into S plus 1 S bar. This is equal to ms divided by square root of S into S plus 1. This is cos theta. These are already studied things. So let us consider, let us come back to our original problem. You have a free electron that is placed in an external magnetic field B0. Now, if S is your spin vector, then the magnitude of the spin vector we know it is equal to root of S into S plus 1 h bar, and S is equal to m s h bar. Now, what is the interaction energy when you have a free electron in an external magnetic field? How can you represent the interaction energy delta E? Here the delta E is given by, it is not delta E, E is given by minus mu dot B0. The interaction energy is E. This is equal to minus mu dot B0. This is equal to E equal to minus mu B0 cos theta. Where mu is the magnetic dipole moment due to spin motion. We can define mu. What is mu? Mu equal to magnetic dipole moment. Due to spin. We have already seen the expression for mu. Mu is nothing but we can write mu, this is equal to minus G E by 2m into S. This is the relation connecting the magnetic dipole moment and the magnitude of the spin. This is equal to minus G into E by 2m into S. If you consider pure spin motion, the value of G is 2. Now we can rewrite this expression as minus G E h bar by 2m into 1 by h bar again S. Now this is equal to minus G into mu B. Mu B is nothing but your Bohr magneton divided by h bar into S. This is your mu. Now if you consider this as equation number 1 and this is equation number 2, and this the value of cos theta, this is equation number 3. Now substituting 2 and 3 in 1, equation 2 and equation 3 in equation 1 implies E equal to minus mu B0 cos theta. Mu is equal to this thing, so we can write G mu B by h bar. Yes, then again B0. Now cos theta is nothing but ms divided by root of S into S plus 1. Okay. E equal to minus mu B cos theta. This is equal to G mu B by h bar. Yes, this is actually B0. Then B0 cos theta is nothing but ms divided by root of s into s plus 1. Also, we have s is equal to root of s into s plus 1 h bar. Now, substituting the value of s here, you will get the expression for the interaction energy E. This is equal to G mu b by h bar root of s into s plus 1, then again B0, then ms divided by here also 1 h bar, ms divided by root of s into s plus 1. So, rearranging the term, we will get G mu b B0 ms. This is the expression for the interaction energy if you have a free electron in an external magnetic field. When you have, if you have a free electron in an external magnetic field. This is the expression for the interaction energy, where mu b is the Bohr magneton, B0 is the applied magnetic field, and ms is the magnetic spin quantum number, and E is the interaction energy. We know that the ms can take two values, that is ms, this is equal to plus or minus half. Now, depending upon the value of ms plus half or minus half, we can define two energies. That is E half, I am saying it as E half. E half, this is equal to G mu b B0. What is ms here? Ms is 1 by 2. So, this is equal to by 2. Then E minus half, this is equal to G mu b minus G mu b B0 by 2. That is, there is a splitting of energy levels. Depending upon the value of ms, your initial energy level will split up into 2. Now, we can represent it like this. This is the case when there is no magnetic field is applied, and with the presence of this magnetic field, this level will split up. Okay. This is for ms equal to half, and this is for ms equal to minus half. Now, corresponding you have when ms equal to plus half, you have the energy E half. What is E half? This is equal to G mu b B0 by 2, and E minus half, this is equal to minus G mu b B0 by 2. So, here B not equal to 0. When B not equal to 0, that means you have a field and you place the free electron in a magnetic field, your energy level will split up into 2. That is, there is a splitting of energy levels depending upon the value of this magnetic spin quantum number. Now, let us revise the definition of ESR. What is ESR? ESR, what actually happens in ESR? In ESR, the paramagnetic material absorb radiation in the microwave frequency and undergo transition between the magnetic energy levels of electron having unpaired spin. So, these are the magnetic energy levels. Magnetic energy levels. Why it is called the magnetic energy levels? Because the energy level splitting is due to the variation in the quantum number ms. Now, what ESR says that when you have a free electron and that is placed in an external magnetic field, your magnetic energy, your energy level will split depending upon the value of ms, and in that situation, if the molecule absorb some radiation, in that case, if the molecule absorbs some radiation, and this is the microwave radiation, this is very important, microwave radiation, and in that particular situation, if the molecule absorb microwave radiation, then naturally there is a transition between these two energy level. There is a transition between the magnetic energy levels. Now, what is the value of h nu? What is h nu? For transition to occur between these two energy level, the supplied energy should be equal to the difference in the energy level. So, you can say that E h nu equal to E half minus E minus half. I am writing this here, that is h nu, this is equal to E half minus E minus half, this is equal to G mu b b0 by 2 minus G mu b b0 by 2, or you can say h nu, this is equal to G mu b b0. So, if you consider an electron in an external magnetic field B0, there is a splitting of energy level corresponding to the different value of ms, and in that case, in that situation, if the molecule absorb microwave radiation, then certainly there is a transition between these two conditions. Now, for the transition to occur, the supplied energy, the energy of the microwave radiation should be G mu b b0, and this condition is called resonance condition. In this condition is called a resonance condition in ESR. This is called a resonance condition. This is the principle of ESR. Here you have to remember that this nu, the frequency of the absorbed radiation in ESR, is in the microwave region. Microwave region.